Okay, welcome back, everybody. Today's Thursday, February 18th. This is flight mechanics class, okay? So let's begin with updates. Not much new updates. The phase 1A, P1A of the course project is due 11 a.m. Tuesday. Tuesday when? Next week? 2 weeks. How come it's 2 weeks away? Something's wrong. Anyways.
It's okay.
Oh, why it's 2 weeks away? So are you going to do something until March 2nd or what? Wait a minute. Something's wrong. Did I make a mistake? This could be Tuesday next week, isn't it? No? What is the reason? I have no idea why I made this decision. You guys tricked me to make this decision.
Yeah, the master presentation.
Okay. Good. Okay. So anyways, P1A and P1B, P1B comes right after P1A. You have to expect that because, I cannot push back everything. So let's just start discussing about P1B, okay? I'm still working on it, so right now we are in Notes B1. I'm thinking of completing Notes B1 unless you purposely sabotage.
Yeah, we do that.
Okay, so we're going to try to finish up Unit B1 today, and then after that, I'm expecting course project to P1B. This is the beginning of the real course project. So before we begin this course project, okay, so P1A is right now, I hope you're going through P1A. This is going to kind of understand what is the baseline of the software you are supposed to be using for this entire semester project, which is X-Flyer 5, which is based on X-Foil. So I think it is important for me that each one of you understand what is the theory behind the software. In other words, otherwise you're going to end up using the software as a black box, which is essentially the same thing I see every year as a high school kids. Design competition, they pick up this software oftentimes. They use it as a black box, literally. And then they come up with all bogus numbers. CD like 25, what are you talking about? Kind of really, they present that in Washington, D.C. I'm the judge and sitting in front of them. I start laughing them. What are you talking? And then they get so nervous because, oh, wait a minute, that professor is doing something. We did something wrong, Oh, it's because we use this software without having any clue what it is. The software spits out 25 of CD, so we use that, kind of thing. Nowadays, I don't make a nasty comments because they're high school kids. It's not you. So if you do the same thing, of course, I'm not going to stay quiet. Lots of nasty comments spits out. Did you really take aerodynamics? Who the hell is the teacher? Kind of statement. Yeah, of course. That's why you are sitting here. You went through aero. Right now, lots of people going through aero, probably many of them probably not going to survive, but anyway. All right, so, okay. So here is the software. So phase 1A is actually quite an important process. In other words, you need to go back to panel method, which is aerodynamics unit C3, okay? So here's a notes given for panel method, and also YouTube lecture is also given for panel method, okay? And then panel method demonstrator is also given. So this is Virginia Tech ENG upgrades. This is a software Java upgrade I actually was involved to develop. This is a very simple code of vortex panel method demonstrator. You are going to basically create your own shape using a bunch of vortex panels. But bunch of vortex panels depends on how many data points you provide. So if you provide very high resolution data points, like creating this shape using, I don't know, 20 data points, 200 data points, 2,000 data points, it's going to create a lot more smoother surface. Okay. But of course, you need to compute tons of computation power for that. If you introduce like a 20,000 data points to create super smooth surface, of course it's reasonably accurate, but you need a computation power for that. Okay, so that's the panel method, which is the very basic theory behind XFOIL. Now, XFOIL 5 is using XFOIL as a batch analysis. In other words, within XFOIL 5, you're going to run series of XFOIL with a different Reynolds number, different angle of attack, different cross section, and you're going to accumulate the database to the airfoil database. If you want to use 2 or more airfoil to create the single wing, you can do so, but you have to run those batch analysis to develop your database to begin with. If you want to use 1 and 2 and 3 cross sections, you need a 3 database to represent 1 and 2 and 3 cross section of a wing. And then you can use those database to shape any shape of your wing, and then you can pitch up and pitch down, predicting your performance. However, that performance Reynolds number range must be covered in the database of 2D airfoil. If you pitch up too much on your wing, that pitch angle and also Reynolds number is not going to be inside of the database you created. Your XFOIL 5 basically says, I cannot interpret your data, I cannot compute anything. Okay? So building the 2D database, something called polar plot, okay, or polar mesh. Sometimes people use those words. Polar. You have to create the polar data. And you have enough polar data database to cover just about any range of Reynolds number and angle of attack of your 3D wing that you're supposed to be designing. Then and only then you can move on. So those are the important things you have to pick up in phase 1A and phase 1B. That's what I'm thinking. Okay? So project phase 1B document I haven't created yet. I'm thinking of what to do. Okay? So this is what I'm thinking what to do. If you want to correct it, please correct me. So project phase 1B, following right after project phase 1A, okay? Project phase 1A is your discovery, exploration, exploratory work, discovery of your software, what it is, and how can we use it, kind of thing. Project 1B, each team, I'm thinking, each team need to come up with your conceptual design, which is what kind of airplane your team want to design. You need to come up with it. There are a few people actually already have a conceptual design, which is constraint. You are SAE team. SAE team actually comes with constraint. My airplane is what's your airplane? Please step in and then take over me for one. What's your airplane? Go ahead.
Well, okay, so we're designing based on a weight limit of 55 pounds.
55 pounds weight
That
limit.
includes payload.
How much payload?
We're aiming for 18 pounds.
18 pounds payload for 55 pounds airplane. Wow, okay.
So it's about half the plane's weight.
Okay.
And then we're also constrained by our wingspan.
Wingspan.
So our maximum wingspan is 10 feet.
10 feet wingspan.
The scoring is also another thing to consider. So for us, our score is divided by the wingspan.
Okay.
So we want it as small as
So
possible.
shorter the better.
Yeah.
So you want to have a very chubby, this kind of wing airplane, carrying hefty amount of payload. And then airplane itself is right way. That's crazy. But that's what you're trying to design.
Yeah.
So your design solution is biplane. That's what it is, right?
Yep.
Okay. So that's SAE team. So each team, please come up with design constraints. What kind of airplane you want to design? Suppose if you have 2 members or 3 members, first of all, each member need to start working on XFOIL 5 and then present to the team, hey, this is my solution for this design constraint. That's the project phase 1B. That's what I'm thinking. So project phase 1B is essentially you start using XFOIL 5 under the certain category or constraint for each team. And then, hey, this is my solution. And then within the team, now it's a competition or argument. Okay, so which one's design is the best? And then move on from there starting from phase 2. That's what I'm thinking. So right now, we are going to focus on main wing, okay? So I think each team can possibly decide what kind of constraint we should put on. Do you have any idea, each team? I want to hear. Or you have no clue? What is it? SAE team has a very crystal clear constraint to begin with. So it's a radio control airplane. Wingspan is this much. And then wing must be lighter, but the heavy payload. Okay, how about you?
Can we set a constraint for stall condition?
You can do that. So what kind of airplane you're thinking?
We were just gonna do a low wing.
Low wing.
With
Low wing means
low
low.
wing, raked wingtips and.
Raked wingtips.
And a cross tail.
Actually, rather than saying that the shape, you should probably start with type of airplane or purpose of the airplane, why we are building. That's probably the better way. In other words, that is the driving factor of the design. The shape comes after it.
Okay, so then I guess
Yeah.
a long range.
Long range.
Yeah, just a long range.
Like how big?
Cargo aircraft.
How big? Manned or unmanned?
Manned
Manned, long range.
cargo aircraft.
High speed or low speed?
Um,
So in a nutshell, what is that airplane? What kind of airplane is that in the category wise? Long range transport, big, heavy, huge airplane, or what is it? So that's no, you don't have to answer that question, but that's something your team need to think about, and then come up with a category of airplane that you want to design and analyze throughout this semester using this software. That's what it is. So if you do a poor job, you're going to suffer throughout the semester, of course. Okay. Well, I will still let you do it, no matter how much suffering you have. I let you do it. And then if you do a good job, you're going to go coasting through. But hey, this is an airplane that guy already has. Wait a minute, why did I even design it? That could be another extreme, okay? Because some of you already have airplanes. Do you want to analyze that airplane? That's also a good idea. But okay. But each team member need to design and optimize and then sell it to the rest of the team. Okay. And then of course you can analyze the airplane to the airplane you already own, and then you can compare. You can do those things. That's fine too. If you're a radio control airplane enthusiast. Okay, so that's something you need to come up with. That's phase 1B. And then as you go through phase 1B, I'm going to let you get started on Xflyer 5, which is mainly wing design. You are going to build the database, and then you're going to start designing your wing. And then design of your wing, you can do lots of things. You can put the taper, you can put the wing sweep, you can modify your wing tip, you can just put the control surfaces, and then lots of things. Okay, so that's project phase 1B. The document it should come up soon. Okay, I'm working on it. Okay, do you have any question here? So today I'm going to, well, I'm under the pressure that I have to finish up like 1 p.m. So let's just take a look at the video. Okay, sit back and relax, and then let's take a look at the video. The video I want to show you is here. Okay. Where? Yeah, this one. Xflyer 5 demo video. You can find it here in course homepage. Go to course materials and this one. So you can see the video. If I cannot finish up the video, you can, of course, finish up by yourself. Let's just take a look at this Xflyer 5 demo video.
In this short video, we're going to be using XFLR5 to make a computation of flow field on a Cessna 182. This is for a homework question.
Now, people online, yeah, this is just someone's number. People online, can you hear and can you follow through the video?
Yeah, I can hear it.
Okay, good. So let's move on. So this is Cessna 182 homework. No, this is not your homework, but anyway, this is just a demo. So it looks like the conditions given. Mass is 1,400 kilogram. Velocity 75 meter per second. Assuming those are density, mu is a viscosity, q is a dynamic pressure, h is a 1,400 meters. So this is altitude and then air conditions. So this actually sets the Reynolds number of your flight condition. And then this is the wing platform area, 16.2 meters square, which is not so big. So this is what? Yeah, this is a Cessna. Yeah, that's right, small airplane. And then root and tip, it's the same NACA 2412, NACA 4-digit standard. That's good. And then this is the root code and tip code, 1.6 from 1.33, so slightly tapered. Lift coefficient is 0.303 for cruising condition, I believe. Reynolds number and root and tip is given. It's like about 7 million for Reynolds number at the root and about 6 million at the tip. So you have to understand, you have to cover the Reynolds number of the wing by, first of all, you need to develop your database. Database is a 2D airfoil cross-section, in this case, NACA 2412. So before you do wing design, you have to run 2D airfoil simulation of NACA 2412, which covers this Reynolds number range well enough so that using that database, you can design your wing, okay? So let's just move on.
In class, and we're going to be doing this by hand in class and as part of your homework, and we're going to also be doing this using computation. So the data is over here. It's a Cessna 182 plane shown here in sort of plan form. The wings on this have a full span of 11 meters. Total plan form area is 16.2 meters, and the wings are made of viscosities of 20 based on
okay.
get polars, essentially the performance polars for the foils of interest. In this problem, we only have one foil of interest, which is the NACA 2412. So I'm going to do an X-foil direct analysis of the NACA 2412. Now you can import foils into XFLR5 just as we did into X-foil in previous class examples. But XFLR5, just as X-foil does, has a built-in ability to do NACA foils internally, and I'm going to do that with design NACA foils. Select my NACA foil. It's a 4-digit 2412 with 150 panels. 150 panels.
So this is a panel message. You have to choose how many
I'm going to save it in here. I'm going to save as a NACA 2412. That's sufficient. You can see that shows up in the menu here. There's only one foil, so I click the menu. I only get one foil and some data down here about the geometry characteristics. Now I'm going to build the 3D wing.
Now you can kind of see, this is the shape. You see that? You cannot see it? Yeah, well, you know.
I can see great.
Yeah, I cannot see here. I don't know why. I can barely see the shape just like this right here. This is the NACA 2412. He basically picked up the data already built into XFlyer 5. If it's a NACA standard 4-digit, you can basically type in the standard 4-digit into XFlyer 5 to read off the shape. Okay, go ahead.
Does Xflyer have any capability for 5-digit as well?
Yeah.
5-digit, yes, they have. So if it's a standard NACA, 4 or 5-digit, or even 6 cities, they do have those database already contained within. Now, suppose if you want to design your cross-section, you can actually import the data, which is leading edge to trailing edge data. Starting from trailing edge, lower surface, go all the way back to trailing edge. Go ahead.
I don't think XFLR5 can do 5 or 6-digit airfoils. I think it's only NACA 4-digit.
NACA 4-digit only. So that means if you want to use 5-digit, you have to import your data. Yeah, okay. Good point. They may fix it for the new versions. I don't know. We can never tell. So let's move on.
Actually, not quite yet. First, I'm going to get the performance polar for this particular aircraft. Foil section 2412. And so I'm going to do analysis, a batch analysis. Now, what I'm going to need in my performance polar is the drag and lift. The drag and lift that airfoil
What's this?
generates in a range of
Ah,
different tack and Reynolds numbers. Now, what XFLR5 does is it's an inviscid solver. It solves for the flow over a 3D wing using an inviscid method, a boundary maze method. And for each of the sections, it will be predicting a lift coefficient, a local lift coefficient for each of the sections. And what it wants to know to get the total drag, so the induced drag it will be computing itself, it also needs to know the profile drag, so that's the skin friction and the viscous pressure drag. And so given the lift coefficient of the local section and the Reynolds number of that local section, it will then go to its X-foil based polar and say, okay, for a 2412 at CL equals say 0.32 and a Reynolds of something like 6 million, what is the drag coefficient? And from its polar, it'll extract that drag coefficient and add it into its total drag.
Do you understand what this guy is talking about? So this guy is basically trying to say that I'm going to build the drag polar, which is a CL/CD plot. And then he wants to compute based on the Reynolds number set from minimum to maximum Reynolds number with the increment. Okay. So this is something called the type 1 Bacci analysis. You can set up the range of Reynolds number, and also you can set up the range of angle of attack alpha. Then you can run it a series of X-foil analysis to come up with the database of drag
for
force.
each of the sections.
Okay.
So you're
So what he does is he just runs it.
0, one of those
There you go.
alphas. Now, if in fact this coincides with the lift coefficient that's needed by XFL R5 at a Reynolds number of 8 million, which is not going to come up in this case, but let's say it did, it would just interpolate between these. So a failure here is fine.
Now you can see sometimes the failure of the data set. In other words, X-Flyer5 says we couldn't iterate. That means, suppose if you go for lower Reynolds number and a high angle of attack, the flow separates over a certain surface, okay? And once the flow separates, you cannot compute. So iteration not possible is normal. In other words, if you set the large Reynolds number range in large angle of attack range, sometimes you have some extreme cases that you have a flow completely separated on top surface, you're not going to have a data computed. So don't worry too much about it.
These later failures tend to be, you'll see some of these will tend to stop converging, and that's simply, it's getting beyond those.
Yeah, non-converging means
So,
that
and
flow
we're not going to
separates.
be in that range anyway. All right, so that's done. Close that. And it puts up these nice kind of polars. Over here, you can see the color.
So you can see those are the color range, those are Reynolds number range. So you're actually running to find out this is a CL/CD plot. You have to rotate 90 degrees to understand what it is. This is called drag polar, right? You have to turn 90 degrees. This is a CD versus CL plot, right? This thing is, okay? And then this only shows the half of it because this is NACA 2412. Yeah, NACA 2412 has a camber. So in order to take a look at the full picture, you need to go the other side too. But anyways, this is CM coded code and alpha plot. You see this just a hump here. This is a transition of Reynolds transition from laminar to turbulent. So you are going to see the transition point right here. Okay. So this is CM coded code alpha plot over the range of alpha from 0 to 20 degrees. Of course, 20 degrees is like a post stall, isn't it? I don't know, depends. So this is a CL alpha plot. Obviously, this is a CL alpha. This is a Rivka slope right here over the range of Reynolds number given. So this is actually CL against XTR top surface. This is XTR is a transition point from laminar to turbulent, which is the top surface. So you're going to compute a bunch of data set. This is going to basically called 2D airfoil database, which is polar mesh. Mesh means you're going to compute over the range of Reynolds number and the range of angle attack. Okay, so you have to do this first for your
Range.
design.
The 4 million is this kind of dark cyan, I would call it. That pinkish color is about 6 million, and that lighter, I'm not sure what I color, light blue, I guess, is 8 million. And you can see our typical plot here. We have the lift, so that's a range of Reynolds numbers from 4 to 8 million by 500,000, and that in the linear part of the lift curve, and this is 2D, the linear part of the lift curve almost identical, right? They're on top of each other, and then they start to separate, and the higher Reynolds number can get to a higher lift coefficient.
That's right. So this is
at
the
this higher
maximum
angle of
CO
attack
point, and the
before
flow
you
begins
start
to
having
separate. So it's going to
a
be like a
decrease in lift
positive
coefficient.
beyond that.
I won't go through all these because we've talked a lot about 2D sections, but you can see here's our typical CLCD X-foil plot and transition plot, and the moment curve here, which is generally plotted in traditional X-foil on top of the CL alpha curve. So that's performance data is done, and now, and you can, if you want, plot just one of these. You can go pick this, and you go polars, and there's current polar, show only certain operating points. So you can kind of filter down if you have too much data. Look at all these angles of attack. If you have too much data, you can kind of filter down. But in this case, we're not really interested in investigating the polars. We're going to move on to the 3D part. So we're going to build a 3D wing. So the next step is File, Wing and Plane Design. So
That's right. So now you're switching to design of wing.
And so I say plane, define a new plane. Okay, so define a new plane. Let's call it Cessna 182. I don't really have.
So this is the wing design panel. So once you complete your 2D database building, so this airplane only uses single NACA 4-digit foil, NACA 2412, isn't it? And then using that database, you're going to now design your wing. Okay. Without your database, you can never design anything. So be careful about that. So you begin with the 2D analysis first, and then you can actually start designing your own wing. Here we go.
Have to name anything particular, but I'm going to. And now you can build in XFLR5. You can build a biplane, which I've never done, but you can build. You can include a body in there. There's a big warning about not including a body, but if you look on the web, you'll see videos of people including bodies. We're not going to do that. We're not making a biplane, and we're actually going to ignore the.
Now, here's a warning, and people use this warning for excuse like, oh, I'm not going to go for fuselage. Well, the reason here of the warning is that once you include the fuselage, your aerodynamic characteristics will alter. We cover that in this class, okay? So your project in this class requires your fuselage. Here we go. So don't worry about that warning sign. I'll let you do it.
Tail altogether. So we're only doing a main wing. So I deactivated.
So right now he's only doing main wing.
Here,
You begin with main wing.
Were deactivated by me.
Phase 1B.
And now, so I'm only keeping the main wing, and now I'm going to define what that is. So it goes into the define menu, wing define menu. And you can see it plotting here as you begin to build it out. It starts with some default section. It's a 1 meter span, half span. So we're assuming it's a symmetric wing. So we're going to define only one side of the wing. In this case, the right side. So I'm going to Y plus positive Y values here for my span. You can put in as many sections as you want. So if we really wanted to build the true Cessna wing, this one, we'd have to put one section out of constant chord here and then taper another section. So I would have 3 data entries here. I'd have the root, I would have that transition point where it transitions from straight to tapered, and then I'd have the tip. And then I would define the wing that way. Now we're using a simpler case here. I'm going to do a 1 section which requires just the root and the tip. Now I'll start with the Y value. So it's the span is 11 meters, so I'm going to have a half span of 5.5. My chord at the root was, I'm going to check what it was, 161 and 133. So I have 1.61 meters here. I have 1.33 meters here. All right, and I'm going to zoom out to see my wing, and you can kind of rotate it around. Now, it has no section shape now. I'm not sure what's even
That's
trying to
right,
show there. A flat wing, I think. So I'm going to pick my foil here.
So right now, it's completely flat wing, right? So you have to introduce what kind of cross-section do you choose for each segment of the wing.
If I had processed multiple foils, I could choose different foils other than the 2412, or you can even start with a 2412 and end with a thinner foil like a 2410. You might think about doing that. Here we're trying to mimic the actual wing as it is in reality, so that's 2412. You have some other options here. Now if I look at this wing from the top, the X direction is the flow direction, so this is the leading edge here, and this is the trailing edge here. And you can see the leading edge is straight, and the reason it's straight is because, well, it's not quite straight. If I make this 0, it'll be exactly straight, and that is the offset. That's how far, so the 0 is always the coordinate of the leading edge of any of these sections. But if I offset a section by some amount, let me just use an extreme example to show you. If I put 5 in here, you can see what happens.
This is a wing sweep, of course. You can offset the location of each cross section to put the wing sweep. This is a linear wing sweep.
So it offsets the tip chords way back, and of course it's making it symmetrical, but I just basically set the X value of the leading edge of the tip chord to 5 meters, and you can see it makes it sort of V-wing things here. Let me put it back to 0. What I would like to do, I think in this simple case, is let's keep the mid-chord, let's put the mid-chord position on a straight line. So the mid-chord of the root is at 1.61 over 2, which is at basically 0.8 meters. So 0.8 meters is here, and I would like the mid-chord of this thing to be at 0.8 meters. So I got to do a little math here. So the middle of that, the middle of the tip is at 0.6665, and I want that to occur at 0.8, so I do 0.8 minus this. So I need an offset of 0.133.
It's just a computing. Don't worry about it. Just a calculator.
Okay, so that basically
Use
is on
Python.
top
No, yeah.
the wing that's
Don't worry about it. This is a calculator.
tapered, and the mid chord is a straight line.
You
So
can
the
do the
middle
same
of
thing
this
with your dumb
section
calculator.
and the middle of this section is lined up in a straight line.
Yeah.
You can also put in here dihedral, which we won't talk. This is for stability. So let's put a little bit in here, make it more like a. Oops. Oh, okay. And should I specify? I should be clear here. So the dihedral is specified at the beginning of the next section. So we only have one section. So the beginning of that is the root. So I put in some dihedral. Looks like this, more like a bird, which I have dihedral. Like a seagull, I guess. So we're not going to put dihedral, and the actual wing has a few degrees of dihedral.
Yeah.
And again, that's a stability thing, which we won't be discussing in class, but we're going to keep it 0.
That's right. So it's a stability thing. So if you want to put the dihedral, of course, you are going to add the directional stability, but that may make your manufacturing guy start screaming. Right? Okay, anyways. So you have, well, everything is a balance.
To simplify things. And you can also twist each section.
Yep.
We only have one section.
Here's a twist. So you can geometrically twist the wing, either way, wash in, wash out. Typically, you need to have a wash out to have like a root stall to begin with. Okay.
Twist is applied to the end of the section. So the root stays still. I'll put some extreme twist in here. Put minus 15 degrees, and you'll see it twist. There it goes. So it only twists the end, and it's linearly interpolating between those. So if we look from the side,
That's right.
sorry,
it's twisted wing.
you can see that the tips are what are called washed out. They're turned down. The root chord is here. This is the leading edge to the left. Leading edge near the origin. This is the tip section, and it's turned down. I put in a negative angle of attack of negative twist angle, and it's washed out. And washing out, some advantages we'll discuss a little bit in class having to do with stall characteristics. It might also, when you go to do your projects, give you some advantage in terms of minimizing induced drag. We are going to put 0 in this case. We're going to mimic the actual wing, which has 0 wash.
Yeah, well, obviously, if you put the wash out or wash in or whatever, how do you create the wing out of the styrofoam? That's the question. In other words, it's a nightmare if you try to hand cut styrofoam just like that with a twist on that. However, in reality, every airplane needs to have a washout, obviously. The reason is tip stall is something that you are going to instantly lose your control at the verge of the stall. So you cannot recover the stall. Okay.
Out. And there we go. So that's our wing section. Now the other thing we want to do is change the paneling. Just as we do in X-foil, where we change the number of points along the section, we can also change the paneling here. Over here, I can click panels, and this menu panels. And you can see the panels, and essentially it's discretizing this vortex lattice method.
So this is called vortex lattice method, BLM. You can choose lifting line theory, LLT, If you choose lifting line theory, LLT, your cross section actually doesn't matter. Okay, so that's the easiest possible way, just the primitive approach. Vortex lattice method is a three-dimensional horseshoe vortex, basically superimposed all the positions of each panel. Okay, we used to cover that theory in L1. Nowadays, I'm not going to do it because no one understands. But if you look at the manual of X-Flyer 5, X-Flyer 5 manual actually explains each method. You can choose each method, but my suggestion to you, okay, which method did you use, by the way, Jessica? 3D panel, right?
Yeah, we used to.
Yeah, you used BLM. Did you use BLM? Are you sure? I thought you used 3D panel. 3D panel is a standard nowadays. Yeah, this guy's using BLM. You can use it, of course, but I would recommend you 3D panel method. Okay, which is essentially almost close to computation fluid type of panel method approach in 3D space. In other words, 2D panel method is going to predict the 2D airfoil, and then 3D panel actually simply extend, stretch out to design your wing. And then, which is most computational intensive method, but you have freedom of lots of design choices. Now, lifting line theory, you cannot even put the wing sweep. That's it. Okay. Anyways, each method comes up with the constraints, but I would recommend you 3D panel method. Okay. This guy's using BLM, but it's okay.
On each of these, in the center of each of these little square panels, rectangular panels, you can see its default clustering is such that it clusters more towards the tips here and here. Section weight speed. So for the homework question, we have a particular cruise speed. We have a particular lift coefficient, which we computed about 0.302, I believe it was.
So this is a type 1 type of analysis, which is a fixed speed. In other words, you want to analyze your airplane based on the fixed velocity which you preset for your design conditions. This is going to actually set the flight condition, and also at the same time, you're going to set difference dimensions, inertia, other thing. Inertia means if you want to actually find out the center of gravity for your airplane for stability purposes, in this class, of course, you need to do that. Okay.
So I'm going to put in the right speed, 75 meters per second. The analysis, these are different methods of doing the computation for...
So here we go. So LLT, this is a BLM, vortex lattice method 1, vortex lattice method 2, 3D panel. You're going to choose 3D panel. Okay.
This case, I think we're going to use with the VLM density.
So this one is aero data. You're going to set the air density and also viscosity. This, it really depends on your flight condition. If you want to analyze based on the sea level, that's fine. If you want to analyze for certain altitude, such as manned airplane, which has certain altitude for cruising condition, you need to modify this. Typically, this is standard sea level, especially for small airplanes. Okay. So you're going to set
964, and the kinematic viscosity was 174. And I think that's all we need to do.
Okay.
So the polar type is a type 1, which is going to be a fixed speed. 1 historic foil does. All right, so it ran. Let me get us to where we want, and then I'll talk about what we're seeing in this plot here.
Can you see anything?
There was a window that popped up, and we'll pop up again.
Too bad.
If you get an error, something about
It's so thin.
that it was unable efficient, and because their chords are changing, they have a little bit different Reynolds number. So for each of these, once it's done with the inviscid solution, it will come back in and say, okay, the lift coefficient of this thing is, say, it's 0.31, and the Reynolds is 7 million. I don't know what it is. And then it'll go to Expo and say, what is, for a lift coefficient of 0.31 and a Reynolds number of 7 million, what is the drag coefficient? And whatever it is, the lookup table will tell it, and it'll apply that to this strip. And then it goes to this one right here, and we'll do the same lookup, and the same lookup. CL is varying, Reynolds is varying, so it has to do for each of these strips. Gets each of the drag coefficients for each of the strips. Now some of the strips are smaller, so it has to take into account the area of that strip being less important than these strips here. And then once it's done with that, it can compute a total profile drag coefficient on there and add it to the induced drag to get the total drag. So that's why it's a two-step process. First, the inviscid flow, then going to its X-foil polar, base polar, to query the profile drag. And it doesn't, I'm trying to say, it isn't fully coupled in the sense that, technically speaking, you have a boundary layer here, and once you went to the X-foil base polar, you could find out what the boundary layers, and the boundary layer thickness would change the pressure distribution. We're sort of ignoring that, or we're taking that into account by assuming that the CL that came out of X-foil was taking that into account. So it's this two-step process, and if we had selected Inviscid in the solver, it would have been a one-step process. It wouldn't bother with any of this X-foil lookup business.
So he's talking about, this is a solver, essentially coupled Euler solution and boundary layer model. Panel method is an Euler solution, okay? So in Aero, we did that. We did the project of the flow of a circular cylinder, which is essentially ideal flow solution. So just the stretch of that idea is called the vortex panel method. Vortex panel method doesn't take into any account of a viscosity. So you're going to have a solution, and then that solution needs to be modified based on two things. One is, of course, boundary layer behavior. If the boundary layer transition separation happens, the solution based on ideal flow needs to be corrected based on that. Number two is, suppose if your flight condition is more than 0.3 Mach number, you're going to correct all the CP data based on Prandtl-Grawert correction factor. Okay, so those two kicks in. It's coming straight from aerodynamics one. Okay, I hope you remember those. Okay.
All right, so then, okay, so we're not quite at the right lift coefficient. It's reported down here, 0.245, so I need to increase the angle of attack. Let's make it 1.5. And it's solving, and I can see I'm at 0.286. And let me try 0.7. Solve, and I'm at 0.302. Okay, it's basically exactly what I wanted for the lift coefficient. Happened at an angle of attack, a geometric angle of attack of this wing of 1.7 degrees. And I'm done with that. And now let's have a look at the solution. So I have, for example, I'd like to see, what would I like to see? I definitely want to see, let's start with, I'm going to kill these panels, and let's do, plot the surfaces. And you can do stuff like change the color if you wanted. You can play around with these kind of things, but we'll leave it green for a second. I want to see where it's transitioning. So I click trans up here, and I can see the transitions occurring.
Can you see it?
And that came from X-foil. It just happened to be plotting it on this
That's the
surface
transition
X-foil.
point from where?
The transition is a little bit later towards the tips here. You can see the Reynolds number is ranging. So you have a Reynolds number highest here and lowest here. So transition's a little further back down here. The lift coefficient may also be affecting the transition. I think that we're going to get a higher lift coefficient towards the root of this wing, which means that these sections are effectively at a higher lift coefficient and a higher Reynolds number, which is why the transition's a little earlier. As we get outboard, our Reynolds number is dropping, and I think our lift coefficient is going to be dropping, so it's going to push the transition back. This is the upper surface, lower surface. Transition is actually pretty similar to the upper surface.
I can't see.
A little, no, about the same. And so that's transition. You can also look at the lift distribution here, and again,
So
we're
this is
looking
span-wise
at the elliptical. It looks fairly
There you go.
elliptical, right, compared to some of the stuff we'll look at in class.
Of course, the best distribution
And
is elliptic.
it's so we have a decent taper ratio, a fairly good elliptical lift distribution. Now it automatically reports for you E, the planform efficiency,
That's right, planform
0.996.
It's how much
so
far away
this
from
automatically. We could do this by hand. That would just be equal to CL squared divided by the induced drag times pi times the aspect ratio, and it should report the aspect ratio. Here it is reporting it right over here. This is all geometry stuff. But it, what was I trying to say? Anyway, so it reports it for you. So this is E. This is that planform efficiency that we discussed in class. Not 100%.
No, it's not the planform efficiency. It's a span efficiency factor E. So it actually computes it based off of the mathematical distribution of an ellipse. How much away from that mathematical distribution is going to be a span efficiency factor. So the if you did the best job, E equal to 1. That's the ideal case. Okay.
But close. We can also look at the downwash. So this is the downwash distribution. It shows it on the trailing edge, so you got to kind of turn the foil around to see it.
This is a downwash distribution, obviously. You have a largest downwash at the wingtip because the downwash is induced from wingtip vortices. You can actually visualize the wingtip vortices formation if you choose to do so. Okay.
This is downwash. It isn't quite a straight line. Again, we're looking for constant downwash. We can see that the downwash is a little bit higher at the tips, which tells me that maybe the tips are loaded too high relative to the structure. Maybe if we wash out the tips a little bit or use a higher taper ratio, we might get closer to a straight line, but it is not bad. It's only really at the ends that we're not quite getting. The center section looks quite straight to me. So in terms of constant downwash, we can also look at the perspective of the span-wise perspective. So this is integrated values along the span. If I double click in here, I have a lot of things I can look at. I'm just going to look at a few. One is the local lift coefficient. So this is a local lift coefficient along the span.
So this is the lift coefficient distribution across the span. And then ideally speaking, this should be an elliptical mathematical function distribution. If so, span efficiency factor is 1. Okay. So you can compute and take a look at those things.
We can see that the lift coefficient, as it does, go to 0 at the tips. So at the tips, we have the condition that the pressure can't jump at the tips. So we have 0 lift coefficient extending up to a maximum, which actually doesn't quite occur at the root. It's a little bit before the root. The whole wing coefficient is 0.3, basically, 303, 0.3.
Now, one thing you have to notice is once you put the fuselage, you are going to have a dip here. Okay. So you're going to see that dip. It is going to also, again, negatively affect on the span efficiency factor here. So you have to design everything based on the balance. If you put the huge, like a fuselage, like a manned airplane, you can't avoid having a dip in the center position here. Okay. And also, this distribution is going to be affected by a range of Reynolds number too. Okay. You can compute all of those things.
So the whole wing coefficient, so this thing must average to this right here, this dashed line or dotted line. So the outboard sections are below, the inboard sections are above in terms of the lift coefficient. So we have higher loading on the inboard, going to 0 at the tips, but a fairly elliptical looking distribution. This is a lift coefficient, but elliptical looking distribution. We can also look at, I wanted to see Reynolds, Reynolds number, range. This is geometrical. So we have root, highest Reynolds number, down to the tips, tapering down to the tips. So that's Reynolds number being used for the profile drag, which I think you can also plot. Total drag coefficient, local drag, viscous drag. That's what I want to see. Okay. So this is the viscous drag coefficient. This is coming from X-foil. And we can see we have our drag coefficient, because the Reynolds number is higher, in the middle is a little bit lower when you get out to these lower Reynolds, and you have a slightly higher drag coefficient. This is not the drag. This is a drag coefficient. So this is being applied to sections. Now these sections are shorter, so even though they have a higher drag coefficient, the actual drag contribution from those won't be as much as it is from these center sections. And the last thing that might be of interest, well, is of interest to your project, where you're going to have a bending moment constraint, is the bending moment. So this shows the bending moment, which goes to 0 at the tips. So these are cantilevered structures, and you have a highest bending moment at the root of a cantilever. And here you have these numbers. We can see exactly what those numbers are by either putting the cursor here or seeing it's about 15,700 Newton meters. And we can also get the raw numbers from the data up top.
So this is basically wing loading based bending moment. So when you attach your wing to the fuselage, of course, you need this kind of dip. you need to have a strong enough attachment of the wing to the fuse rod. So this actually comes into play later stage of your design process that you actually start thinking about literally manufacturing this airplane based off of the X-5 analysis. So this is the bending moment. So you need to be, well, you cannot use like a plywood here. You have to use aluminum bar kind of thing. You know, you have to design those manufacturing process.
Let me see if there's anything else I want to mention first. I don't think so. So if we go up here, we can go to operating point. So this is this one operating point that gives us our lift coefficient of 0.3. Properties. From my properties, I can get more digits of accuracy in terms of things that I need. So I have here, and particularly these first four numbers are important. The lift coefficient we ended up with, that's the whole plane lift, or the whole wing lift coefficient. The entire drag coefficient, 0.00912, and so this is a 91 counts. We have our viscous drag component, and this comes from the X-foil part. This is viscous pressure drag and skin friction together on the wing. About 52 of those 91, and I have 38 of those 91 coming from the induced drag, the I stand.
So he's using drag count. Do you remember that? 52 drag counts in CD 0.00052. It's a 52 count drag. So this is an operating point. You can actually set as many as like lots of operating points you're interested. Suppose this is an operating point of an airplane for cruising condition, takeoff condition, landing condition. You can set out of those operating points, you can squeeze out point-wise data for the detailed CD, CM, CD, CL, other things. Okay, so this is the operating data point you can store.
Stands for induced. Induced, viscous, total, and lift coefficient. So those are key numbers right here. It doesn't report the max bending moment here, which would actually be nice. You can get the real number for this if you'd like it from operating point export, and I can dump all this into a table. I'll just overwrite something I have here. I'm not sure what this is. I'm going to overwrite this text file. Hopefully that wasn't important. And I'll go back in and I will open that up so you can see what it looks like. And I think it was right here. Okay. And so I have similar information up here with those drag coefficients induced and the viscous pressure drag, or this P stands for profile.
So this is the computed data based off of the how many panels do you have. So suppose if you choose the 3D panel method, and then if you choose to go for like 1 million panel, you have a 1 million data sets coming up. Okay, so let's be careful about that. So this software, you can go for any resolution, but if you go for like a too high resolution, each data could be like a 10 gig. And then if you spits out, it's just a number of the number. You can never tell. I mean, only thing you need is just the integrated effect. So what is the performance? CL, CD, CM, CM protocol, CMAC, other things. And then this software can easily dominate your computer, right? So sometimes you want to have a supercomputer because it's going to take forever to compute one operating point. The reason is, well, you're using like 1 million data points. I don't know. Anyways, so
CD, induced CD, total CD, some moments and things you might need. Actually, I'm noticing, which I did not notice before, it does report right here the maximum bending moment on the wing. Now this data file is big. It has all this kind of span-wise variation stuff that it plots in these plots we've been discussing, and it also has all the data, pressure coefficient data for the entire wing, for all the cells in the wing, if you wanted to reconstruct something. And I'm not sure there's anything necessary here, but the key out of here is this bending moment was about 15,600 Newton meters. So we'll end that there. Actually, let me just grab, just check once again these properties. And so I'm just going to copy and paste these so I have them, and I'll need them for the homework. So this is
okay. So do you have any questions here? So this is something you can start from as a team. Okay. So this video is again posted here, so you can go over it by yourself and then try to understand. Okay, what this software does. It's based on vortex panel method, which is if you really want to take a cross look at vortex panel method from aerodynamics, it's note C3. This is all about vortex panel method. So I try to cover as much as detail. This is a theory based on this X-Trial 5, aka X-foil batch processing. Okay. So please work on your project phase 1A, because this is what? This is due March. Okay. So I don't know why I made that decision, but the project phase 1B follows shortly after that. Don't expect like another week dumped in, before phase 1B comes in. So you actually start working on it, okay? And then I think the first thing first, each team need to come up with a constraint of what kind of airplane you want to pursue. So this is a category of airplane comes with constraints like the size and the mission and the performance requirements and other things. You have to come up with a common, like a short documentation shared within your team. And then at this phase 1B, I want each member do a unique sets of analysis and also design decisions, and based on the design decision you're going to analyze, and then later on as a team get together, compare each other. Okay, your design is better, or my design is better, kind of argument. So as a team you're going to pick up a best design and move from there. Okay, more detailed analysis. That's what I'm thinking. Okay, so let's stop here today. Any question? People online also, any question?
Nope.
Nope. Okay. All right. So have a wonderful weekend, and then see you guys next Tuesday. All right.
Which is,